Alrighty, in this video we are looking at function operations. Our objectives are to find the sum, difference, product, and quotient of functions, and define the composition of functions. Let's begin with defining what a function is. A function is just a relation used to model inputs and outputs for a particular phenomenon. So it's a mathematical way of expressing something that we see in nature or we're recognizing in a particular situation. One such phenomenon that we're going to be looking closely at and modeling in this chapter is music. In some functions that we're going to see very shortly, we are able to actually measure sound. So that's one example of how functions can be used. I like to think of functions as a machine. Each of these machines has a specific function or job that it needs to carry out. Here's a kind of visual illustration for you. Let's say that we were going to add two functions, f and g. That can be illustrated as taking the function f at a particular value and finding its output, taking the function g at a particular value and finding that output, and then just adding the outputs together. And that's what you're seeing modeled with the function f and g for the value 4. We evaluated each of them separately and then added the outputs together. There are actually 4 different kinds of operations that we're going to work with in this video: addition, subtraction, multiplication, and division. And the way that they are expressed here, we need to become very familiar with. You'll usually see it expressed like you see on the left, but we know that the rule for that particular operation is then on the right. So if you're working with f plus g of x, it's really just the function f plus the function g. If you have f minus g of x, it's the function f minus the function g. If you have f times g of x, you just take those two functions and multiply them together. Similarly, if you have f divided by g of x, it's the function f divided by g. Now, the only stipulation there with division is that g of x, that denominator, you cannot let that equal 0. So let's go ahead and look at some examples together. In this example 1, we're going to do addition of the function f and function g. And then we're going to write the rule. The rule is just the equation. That would be the result of this operation. So f plus g of x. We need to remember that that rule is really just the function f plus the function g. So we can rewrite this. F plus g of x is the same thing as our f function, which is x plus 1 squared. And then add to that your g function, which is x minus 2. You have a binomial squared there, which means you need to sing the song. You take the first term, square it, that's x squared. Take the second term, square it, and that is 1. Take the first times the second. 1 times x is x, times 2 gives you 2x. So we've simplified that squaring, and now we just need to combine like terms. That would be x squared. You would have 3 x's and then minus 1. So that is the new rule representing the sum of those functions. Let's do similarly for subtraction. When you're working with f minus g of x, remember that that is the function f minus the function g. Let's rewrite it. That would be the function f, which is x plus 1 squared, minus the function g, which is x minus 2. Again, we have to sing the song and expand that squared binomial, and then very carefully combine like terms by subtracting. It would be x squared, 2x minus x is just x, and then that last term, 1, it would be minus negative 2. 1 minus a negative is actually plus, so that gives us 3. And that is subtraction. Now let's look at multiplication, finding the product of two polynomials, of two functions, I should say. The function rule says, well, if you're multiplying f and g, it's really just multiplying those two functions. So we can rewrite this, and you have x plus 1 squared times x minus 2. Again, we sing the song to expand out that binomial squared. And then I like to use this process of old school multiplication to multiply these larger polynomials, because you can't just FOIL. So that would be negative 2 times 1, which is negative 2. Negative 2 times 2x, which is negative 4. And negative 2 times x squared, negative 2x squared. Now we're going to move on to multiplying the next, which is the x times everything in that top part. So that would be x times 1, which is x times 2x, which is 2x squared, and x times x squared, which is x cubed. Now we will combine like terms using addition, and it will be, you'll have just 1x cubed. The x squares actually cancel out. If you have negative 4 and a 1, that's going to be 3x and then the 2. I'm going to simplify that because there's no need to write 0x squared. So the product for f and g is x cubed minus 3x minus 2. And that is multiplication. Lastly, division. This one, actually, you might be thinking it is going to be the hardest, but it is pretty straightforward. All we're going to do is express our result as the ratio of our function f over the function g. So that looks like the function f, which is x plus 1 squared, over our function g, which is x minus 2. That's it. The only thing that we need to note in addition to this is what would make our denominator equal 0, because that is not permissible. You cannot divide by 0. So we have to include that x cannot be equal to 2, because if you plugged a 2 into the denominator, it would be dividing by 0, which is undefined. So there you have it. That is all you would need to do for dividing functions. There's another operation. It's called the composition. The composition of two functions, f and g, you would denote f and then a little kind of circle, and g. You would read that f, the composition of f and g. And you define that as f of g of x. Once again, you read that f of g of x. So the composition of f and g is really f of g of x. Now that might be really weird looking, so let's try and use an illustration to help us out here. The composition of two functions, you can think about it as machines in a series. You take the first function, the one that was on the very inside, and the result of that, so you see we took 5, plugged it into our g function, and that gives you 11. That output becomes the input for that function on the outside, your second machine. And so you plug 11 in there, and that gives you your composition of your function. That actually tells you what f of g of x would be equal to. All right, why don't we do an example together similar to this where we have values. So we're going to evaluate the expression f of g at 2 when f of x is x squared plus 3 and g of x is 2x plus 1. We need to rewrite this so that we better understand what is being plugged in where. F of g at 2 could be rewritten as the function f of g at 2. So we have to start kind of like in that inside part. We need to figure out what is g at 2. What would be the output of our g function at x equaling 2? And that's going to be the input for f. So g at 2, that would be 2 times 2 plus 1, which is 5. Now take that value, that is going to be plugged into the function f. See, f at g of 2, we know what g of 2 is. G of 2 is 5, so plug that in to your f function, 5 squared plus 3. And that gives you 25 plus 3, which is 28. And there you have it. That is evaluating a composition of functions. Pretty cool. Sometimes, though, you won't be asked to evaluate. You'll be asked to just give the rule. So you're not going to actually have a value that you plug in. We use the same kind of setup, though. We're going to substitute g of x into the f function because the rule says f of g of x is f, and then inside of f you plug in g of x. So that looks like f, and then for that input, our input is our g function, which is 2x plus 1. So in the x position, in the input of your f function, you have to plug in that binomial. So that would be, instead of x squared, we plug in the g function, which is 2x plus 1 squared, and then add 3. We can sing our song and expand that out, that binomial squared, or we can write that 2 times and use distribution. But you would get 4x squared plus 4x plus 1, and then that plus 3 at the end. Simplifying would give us 4x squared plus 4x plus 4. That is the rule that represents our new function after, really, it's kind of like the movie Inception. It's like a dream inside of a dream. Well, it's a function inside of a function. Your function has become the input for another function, creating a brand new rule, a brand new machine, a brand new function. So there you have it. I hope you all enjoyed.